Welcome back to the ARSET training, large-scale applications of machine learning using remote sensing for building agriculture solutions. My name is Sean McCartney, and I'm an ARSET trainer based out of NASA's Goddard Space Flight Center in Greenbelt, Maryland. I want to welcome you all to the second part of the three-part webinar series. The following slides provide an overview of the three-part webinar series. The motivations for hosting this training topic are that timely and accurate in-season crop maps at local to regional scales is crucial for agricultural decision-making and management. Irregularly spaced time series are common with optical satellite images. Training robust models on remote sensing data often requires very large data, but processing and training is complex. The cropland data layer provided by the United States Department of Agriculture's National Agricultural Statistics Service only gives estimates of the types of crops released to the public a few months after the end of the growing season, and not their sequence or timing, for example, double cropping. By the end of this training series, participants will be able to use recommended techniques to download and process remote sensing data from Sentinel-2 and the cropland data layer at large scales with cloud tools, produce interactive plots and maps, tables, time series for investigation and verification of data and models, filter data from both the measured and target domains to serve modeling objectives based on quality factors, land classification, area of interest overlap, and geographical location, build training type pipelines in Tensorflow to train machine learning algorithms on large-scale remote sensing geospatial datasets for agricultural monitoring, and utilize random sampling techniques to build robustness into a predictive algorithm while avoiding information leakage across training, validation, and testing splits. The prerequisites for the second part of this training are a general understanding of Python programming in Databricks from Part 1, access to the associated data from Part 1, and to sign up for and access the Databricks Community Edition. A link to sign up for the Databricks Community Edition is provided on the slide. Over these 3 weeks, there will be 3 1.5-hour sessions, which will include presentations, demonstrations, and question and answer sessions. All materials, code, and recordings from each session will be available from the training webpage. If you are not able to attend one part, a recording will be made available within 48 hours of the training day on the ARSET website. Homework opens on March 19th and will be due on April 1st. You will be able to access the homework from the training page starting on March 19th. A certificate of completion will be awarded to those who attend all live sessions and complete the homework assignment before the given due date. Please put your questions in the question box and we will address them at the end of the webinar. Feel free to enter your questions as we go. We will try to get to all the questions during the question and answer session after the presentations and demonstrations have concluded. The remainder of the questions will be answered in the Q&A document, which will be posted to the training website prior to the start of next week's training. I will now pass the presentation over to our guest instructors for this webinar series, Dr. John Just and Erik Sorensen from John Deere. John and Erik, over to you.
Okay, thank you all for joining us again for part 2 in our series on large-scale applications of machine learning using remote sensing for building agriculture solutions. This part is on data loaders for training ML models on irregularly spaced time series. So our focus here is on imagery specifically as a data source. I'll be the speaker for the PowerPoint presentation or the slide deck part of this, and my name is John Just. I'm a principal data scientist at John Deere. I'm also affiliate faculty at Iowa State University in the Agricultural and Biosystems Engineering Department. Joining me is also Erik Sorensen. Erik, can you introduce yourself?
Yep. Hi, everyone. My name is Erik. I'm a senior data scientist at John Deere, and I'll be giving the demo of the code in this part.
Thank you, Erik. Some objectives for this part we have for everyone is that by the end, you'll be able to use Python and Databricks Community Edition to understand how to split the data that we have into different parts, in this case, a training, validation, and test set, and that's specifically for during the experiment to avoid data leakage that could affect performance of the model. We also look to teach everyone how to build, this is the core part of it, a specialized optimized queue called a data loader. Really, we're going to use TensorFlow, but that's really what a data loader is. It's just an optimized queue. And what it'll do is it'll extract and basically use the Parquet files that we built in part 1 with all the data. We'll be able to filter some data that we want to ignore. We'll apply some augmentations that help to form the data so that it's more optimal for modeling purposes. And we'll bucketize it then into a regularly spaced time series from an irregularly spaced time series. So that will make it more conducive to using typical model types. And finally, we'll normalize the values, and that will again be part of the optimization process so that we can get a robust convergence during training. And then finally, we'll show a little bit of information regarding how the queue is optimized for speed by using parallelization. Some prior knowledge review. We are really working with satellite imagery for the most part here, and there's a high amount of irregularity due to things like cloud cover. The cropland data layer, which is a source of our ground truth, provides labels that we can use as targets during training. It's covering the continental United States, and it's released once a year at the end of the year. So we have this, generally speaking, for the last 20 years or so in the United States of data. We do store data in the previous section or the previous part. We showed how we stored data as byte strings and Parquet files. It's not a human readable format, but it allows for efficient storage of very large data, and then it also is smaller and helps the load time be faster from disk. All right, so let's get into section 1 of this part. This is about generally TensorFlow and how data flow works within kind of a process to train models. So as an overview, TensorFlow itself, it's an open source library from Google. It has quite a few capabilities. We don't use all of them in this demo. Some of those, like deploying models and implementing ML ops, are really focused on production deployments and maintaining models over time. So those are nice capabilities for when you are moving to that large scale deployment. Part 2, this part, is focused on preparing the data. So this is where the queue comes in, or the data loader comes in. And then part 3, next time, we're going to focus on building ML models. So that's a little bit of an overview of what we're planning and how it fits into TensorFlow's capabilities. As far as data flow is concerned, we have 3 parts to this series, and really the first part was focused on getting the data that we're going to use to model with, and so we did go over, in that case, getting the CDL data. We focused on processing the satellite imagery at scale, and so we got it into a form that was kind of conducive to modeling as a time series. Now for this part, we're at the part where we're going to use TensorFlow's data module, and this is going to really specifically focus on the extract, transform, and load functionality of TensorFlow. So those are part of we call that ETL, oftentimes as an abbreviation, but those are part of all part of the data model within TensorFlow's data loaders. And then the third part will again focus on model training and inference. We'll specifically use TensorFlow's Keras in this case. All right, so section 2, we'll talk a little bit about these TensorFlow data pipelines. There's a lot that could be said about these functions. Again, this is really an optimized queue. So instead of building a queue from scratch that has all the capabilities we would want, TensorFlow has done a great job of kind of giving the functionality in a much nicer form, and it's really quite simple compared to building your own. There's some links we've provided here where you could go learn a lot more about each of the options when putting together one of these data loaders. But at a high level, there's kind of a general suggested workflow that we follow here. And so this really first of all, you have to have some kind of list of file paths, or you have to have your data in some form that you're going to essentially turn into a data set that we're then going to load. So in this case, it could be a list of file paths, but we also in this particular data, this tutorial, this demo, we actually load all the tables into memory, and our specific sample will not be a file, but it will actually be a row in memory, a row from the table. So and this is a little bit faster when it's possible to do that, since you already have it in memory, you don't have to read from disk. So from there, once we have this list or this data set kind of specified, there's a bunch of dot notation methods we can use on that particular data set to essentially apply functions that are pretty typically desired in a data loader. Some of those we mentioned were like filtering. So if there's particular data that's in our data set that we don't want to use or has some issues with it, instead of pre-filtering that, we allow we kind of have this option to dynamically filter that out during training, because it may change over time, and trying to apply that on the data set prior to training may be kind of a hassle. So this is a nice function that we will use here as well. Shuffling the data is another function that we often use, and it's highly recommended to shuffle your data so that you diversify the samples in each batch and ultimately get more robust gradient updates to your model. The map function is a very important piece where essentially a lot of the bulk of the work is done. That's where we're parsing the data, and we're applying a lot of that transformation to the data to get it into a format where it's really kind of going to load and be ready to be put into a model. And then we have our targets as well there in the right format. And then a couple final functions that we use and that are often used. You're going to have a batch of some kind, so you specify the batch size for each batch, and then we're going to have prefetch as well, which this is kind of essentially specifying a background set of processes, so that while the main process is doing the training, the background processes can be doing the process, the ETL, the extract, transform, and load to the data and have it ready. So there's very minimal wait time when we need new data. This is an example implementation of that. So in TensorFlow code, you might have some list of files. This has been specified as a TensorFlow data set, and so it's a data set object. We can apply a filter to something. So in this case, an example could be we're trying to filter double crops because we don't want to train on double crops in this case for some reason or whatever. Shuffling, you got to specify some type of size to the buffer of the shuffle buffer. So in this case, usually you want to make that the size of the data set. If you can. If you don't have enough room to do that, then there's other ways to get around this. But typically speaking, you probably want this to be big enough to shuffle your entire data set. The map function here in this case uses a lambda format where we kind of have a parse function here, and we have the ability to actually specify parallel processing. So we have a number of parallel calls. You could put a number in here, or you could let TensorFlow itself, like what's being done here, tune that number. Then again, dot batch and dot prefetch, and prefetch again specifies in some sense the number of background processes that might be going on to load your data in parallel with the main training process. So you could also use an auto tune argument here instead of just specifying it, and let TensorFlow figure out what is optimal. I want to specifically focus in on the map function, since that, again, is where the bulk of the work is done. The other pieces like filter, batch, and prefetch are really pretty straightforward. Map is where it can get very custom what you want to do here. In this case, we have some things like, we might want to be reading from Parquet files. If we already have it in memory, we still have to use things like TF-IO decode raw. This is actually going to essentially take those byte strings that are very, that are essentially not in a form to model. We're going to convert those to typical numbers or arrays or whatever that we need to actually work with that data. We're also going to do a lot of the work to bucketize the data. So there'll be some custom functions we need in there because when we break the data up into regular intervals, there may be 0 to some number greater than 1 of images in any one bucket, and we have to do a selection process. We'll do some normalization of the data, encode the labels in one-hot encoding. Again, this is part of just the standard format for training models, and we'll return it as a tuple of data. And so this is the map function can do all this, and it can do it in parallel. So it's quite a powerful function. Specifically, I just wanted to highlight the way that we are decoding the byte strings. When you look at the table that the data is stored in, it's stored in really kind of what looks like unreadable text strings. And the reason these show up like this, so if you look at the bands column, which actually should be the values associated with the different bands in each scene that we processed per pixel, you see like really an unreadable string of characters. That's because that's how a byte string shows up when you actually try to view it. So we need to decode that into real numbers. And so when we decode it, we get numbers back that are clearly what we would expect for band values for Sentinel-2. So that's pretty straightforward to do by just using TensorFlow's decode raw button, or decode raw function, sorry. There's a few things that are expected, like you have to actually specify the number of bytes and the data type, but this is all fairly straightforward, and it can work with arrays pretty easily as well, which is kind of how we want the band data to be decoded, for instance. All right. Section 3. So now we're going to go through exactly what's entailed in preparing the data set. So we've kind of covered generally how we use TensorFlow data sets and some of the main functions and methods available. Now we'll talk about what we're actually focusing on for this data. First of all, one of the most important pieces of the particular data that we're using, but this is more general than just our data. We need to split the data into train, validation, and test sets. This is not specific to time series data. This is done for any type of data source. The reason for this is that we use these validation and test data sets for things other than training a model. Specifically, the validation data set can be used to avoid overfitting for tuning hyperparameters, and then the test data set can be used to gauge real world performance. Really, all of this translates to we're trying to get the best performance out of the model were it to be applied in production or generalized to new data that wasn't seen. A common split of the data could be that you're putting 80% of it towards training, and then reserving 10% for validation and another 10% for test. This can vary, but generally speaking, you're putting a lot more into your training than you are into the other two. But you're reserving something that's enough to get a good convergence of your model, and also test the generalization performance. So this is somewhat shown by this curve here. The validation data set is essentially reserved so that oftentimes what will happen is your model can overfit to the training data, and you won't even know that it's actually happening. But if you're watching during training your validation data and how your model is performing on the validation data, which is not being used to perform gradient updates, you'll see a point where it kind of bottoms in the performance of it, and then the performance actually starts to get worse. So in this case, the loss is the whatever the metric is we're using to judge the model performance, and at some point it hits an optimal value on the validation data and then starts to increase. And this is the point where you'd want to stop training the model. You don't monitor the training data set, because generally speaking, the training loss will continue to decrease if you keep training. So specifically for crop type prediction, what we really care about is not leaking information across time and space. This is a very subtle but important point. When you split the data with satellite imagery or any type of data set that has some spatial and temporal component to it, you want to make sure not to leak that data by essentially using some type of data in the training data set that may also somehow be very highly correlated with training in the validation or test data sets for some reason. So that could look like sampling data from nearby locations from the same year. So we already know that generally speaking, agricultural practices will be very similar when you're looking at places in certain areas that are close together and over the same time frame. So like if we're looking at like a specific 10-mile radius of one point, you expect all the farming practices within a 10-mile radius of a specific point to be more similar than places that are hundreds of miles away. And the same is true across years. So generally the weather conditions from one year to another can change a lot, but they're fairly similar within 1 year. So you will see that by splitting the data in some way that avoids leaking that information, you'll actually test the model performance better. In this case, the way that we handle this is we're looking really at the same area for training, validation, and test, but we're splitting it across years. And this is one way that's convenient, and it also actually is fairly effective at training models that are fairly robust and then testing their performance. Another important thing that we have to do is normalize the data. This is really required for the optimization procedure, not much of anything else. So the band values for satellite imagery are, this is an example right here of a box plot of the different 12 different band values from Sentinel-2. They really have wide ranges and they're different for each band. If we were to try to optimize on these directly, so input these into the model and then let the model learn its weights and biases based on these particular values of bands, it will not actually achieve very good convergence during the training and optimization process. So in order to get good convergence or optimal convergence, what we need to do is we need to actually normalize each of these bands individually by subtracting the mean and then dividing by the standard deviation. So at that point, each of these bands will essentially have a very similar distribution. Now, there might be some different skewing characteristics on each of them, but at the very least, the mean and the standard deviation are very similar, and this ends up producing pretty good results in optimization in practice. So as an example, I took the VRE2 band here, and so I normalized this, and I went from ranges and values in the thousands down to a mean of 0 and a standard deviation of 1. Bucketizing is another key component of this work. This is actually how the cropland data layer does things as well. I believe they bucketize their data in time intervals of 2 weeks. Here, this is just an example, but we're bucketizing on an interval of 5 days. So in this case, this example shows that we have a time series of data. We've got some data available over this time frame. And so let's take a time frame of 45 days. We're going to go from April 10th all the way to May 25th. And what we're going to do then is we're going to try to actually add in, we're split into basically five-day increment buckets. And so when we do that, we need to have a value in each of those increments. So if the data we actually have available is only on these specific dates, what we're going to have to do is basically fill in or pad some values where we did not have a scene available to get some in that interval to get some type of value. So in this case, we had a value available on, for instance, April 10th. We didn't have values available on the 15th and 20th. But then when we go to, again, the 25th and the 30th of April, we had some values as well as the 5th of May, et cetera, et cetera. So we begin to pad values in here. And in this case, we're padding in zeros. That's what we do here. That essentially amounts to, I kind of talk about it in the next slide, but when you've normalized all the data, a value of 0 is really the mean value. So you're kind of padding with mean values here. And this works sufficiently well. There's no perfect solution here. One could try to interpolate values of some kind, but that also gets kind of tricky. So we find this works quite well. So again, kind of a view from a plotting standpoint of bucketizing the data. Here, we would have taken an interval over 45 days, and we've essentially, or over, sorry, not 45 days. In this case, it's a 180-day time frame. We had available 38 images. This is a real-world example. We had available 38 images, and so by the time we actually split this into intervals, we find that these kind of gold-colored dots at the bottom here, they're all set to 0. Those are the intervals where we didn't have an available satellite image, but these other ones that are colored, those are where we actually had a value. And so we're showing this via in this case, the NDVI curve over this time frame. But this is kind of a visual of how we would pad and where we would see these zeros entered in. The actual values, of course, of these are going to be normalized as well. So there will be some value, that's more like the range we saw when I was normalizing data back here. They'll be somewhere in this range for each band value. So, and we'll have 12 bands available for each of these. So in this case, when there were zeros, all 12 band values would get a value of 0. But when there's actually a scene available, they will get the values from that scene. Okay. Another thing we do that's, again, this is somewhat subtle, but we do want to avoid trying to classify a crop, because we're doing this in real time. Our goal here is to classify crop types in real time. It's not just what happened over the entire year. Because of that, it means that we could be trying to classify a crop at times when there's nothing growing. So if we look at earlier in the year, this would be January, in this case, January 2021, moving into all the way up to somewhere in probably around May 2021. There's really nothing growing during this time frame. In this case, the gold-colored dots are really signaling that the scene classification layer from Sentinel-2 is identifying that there's no vegetation present. The scene classification layer is actually fairly precise when it comes to identifying if vegetation is growing or not. So we can actually use this for our real-time predictions and essentially filter to times when vegetation is present and make that when we predict. If we can use the CDL and we see that there's not really any vegetation present for our particular application, then we can just ignore predicting at that point. Or we could apply some type of filter that requires vegetation having been present within some time frame. One of the reasons to do that would be sometimes there are cirrus-like clouds that get into the mix. That's what these blue dots here are. And so that can cause some specific time interval to not have maybe the view of the ground, the surface, and get an accurate estimate of if vegetation is on the surface or not. But for the most part, this is a very effective way to help identify when we might want to be actually predicting, and also avoid trying to train the model to identify. So if we use the target of the CDL for this particular field, the CDL obviously has looked at the entire year to make that prediction. And if we were trying to predict the crop type using only data from the springtime here, the model really shouldn't be able to identify what type of crop that is. So it could be actually adding in bad gradients to the model if we try to use some of this data along with the training target to train the model. So we do want to ignore this during training for that reason. Okay. And now we'll talk a little bit about how we've taken the CDL values and boiled them down into some of the classes we care to work with. The CDL actually has quite a few numbers of labels, more than 100 that you could actually find, but we really don't have all those labels available, or at least we don't have sufficient data for all those different categories available from the area we're looking at. So we really want to focus in on maybe where there's some classes or categories that have sufficient data and that we might be more interested in, and then for the other areas we can kind of group them together into other classifications. So an example of that could be we have quite a bit of data from corn, soybeans, cotton, and rice. We showed some of that in part 1 of this series, some of the data distributions, and the other crops that are out there, really, we don't have, like an example that could be peanuts. We don't have a ton of that, so we will just generally group those into cultivated areas. And then besides that, those categories or those specific categories of these crops, and then a general crop category, we reserve another one for uncultivated areas in case there's like developed area within there that we sampled, or something that's water, or something that's just not really a cultivated area. And then the final value is, we talked about this earlier, but there could be an area where there's just no crop growing, but it doesn't fit into the uncultivated area, so we may just want to say that right now there's no crop growing, but there could be in the future. Okay, so that by doing so, we reduce the number of categories we need to predict from hundreds down to around 6. This is highly customizable. This is what we do for this example, but you can obviously modify this to fit whatever you would like to do for your application. Some of the mappings, again, more specifically speaking, the labels we're looking at that we want to focus on from a crop standpoint are corn, soybeans, cotton, and rice. Some other crops that are present in our data are shown here. We don't have a lot of it, so we're going to kind of just group those into a general category. Uncultivated area, again, is anything that doesn't fall into these other categories here, where it's not a crop, it's not a cultivated area at all. So this could be grassland, it could be water, it could be urban area, something like that. So our final training list of labels looks like this, and this is how we end up essentially outputting the labels from our model. And one note about the way that these labels are formed when you're training a model, the way that the models work is there's a specific dimensionality to the output. So if we have 6 labels that we want to predict, in this case, we might be predicting these 6 labels here, and then the default is no crop growing if the scene classification layer doesn't have any vegetation present. But we'll predict, so if our dimensionality is 6, we will actually, for classification, do what's called one-hot encoding. One-hot encoding essentially says, all right, whatever the class is, we're going to label that as a 1. Everything else gets a 0. So if the CDL label for this particular row or this particular area, if we have a pixel that was corn for 2019, for instance, and that's in our training data, we would essentially get a label that's it's got 6 elements, and this one, if this was our corn element, that one would get a 1. And so you can just see how this works here. So again, if we've got indexes 0 through 5 for 6 elements, one of those indexes, so index 0 could be uncultivated area, index 1 could be cultivated, index 2 could be corn, and etc. And then it gets a 1 depending on what the CDL was specified for that year. And that concludes the slide deck part of this presentation. We're going to move after this into the demo, where Erik will show everyone how to do all of this in DataBridge Community Edition with Python and TensorFlow. Thanks. Erik?
Thanks, John. Yep, I will be given the demo of the code for part 2 in Databricks. So just a reminder, we'll be using Databricks Community Edition. You will need to set up an account if you wanted to follow along and run the code. To run the code in Databricks Community Edition, and all the instructions will be on the web page. To load the part 2 code, we'll provide a Python file that you can upload into Databricks Community Edition by going into your workspace, navigating to kind of your user file, and then right-clicking here, and then clicking the import, where you can drop a file from your local computer that will upload it into the Databricks workspace. Once you're in there, then you can click into the file, and then you should be all set to go to run the demo. So one quick note, if you recall from part 1, we do have to kind of create a cluster, a Databricks cluster that will be the compute that runs the actual code in the notebook. One change is in part 2, I ran this with the DBR 13.3 LTS software version of Databricks Runtime. This might work with other versions, but your success may differ. But this should be guaranteed to run using the 13.3 LTS. And to set that up on your cluster, when you go to create your cluster, you can just specify the runtime that you want to use, and you can specify the 13.3 LTS, and then create the cluster. I already have a cluster spun up, so we should be good to go. And I did pre-run this notebook in the interest of time. We will be installing 2 packages with pip. The main 2 packages is Tensorflow and Tensorflow IO with these specified versions. These are the only other required dependencies that are not pre-installed on the cluster to be able to run the notebook. From there, we'll also import the other necessary functions to run the code. So, okay, the first step is we'll need to load the data that we processed in part 1. These data files were saved as zip files, and they are also available in the training website. To upload these into Databricks, again, you can go into kind of the catalog section, go into DBFS, and you'll see another file kind of structure directory, store them. You go into the file store. I uploaded them into tables, and then you can upload, click the upload button, and then kind of drop those zip files in here, and they will upload into this table directory and will persist into the Databricks file store. And so anytime that you kind of come back into Databricks, your files will be saved there anytime you log in. So after those files are uploaded, we can kind of run this command. This is a way, kind of a pre-built command in Databricks to kind of list files in the Databricks file store. And we can see when I go to the file store tables, we can see the 2 files, the 2 zip files exist that we created in part 1. They exist now in our file store, and I can use them to create the data loader for this part 2 example. First, before we can do any processing of the data, we need to copy these files into the local driver node, which is the cluster compute file system. And so we can do that using the Databricks utils file store copy command, where we're copying from the Databricks file store into the local file system of the driver node. Once we do that, we will need to unzip these files into their native Parquet format. And we can do that using just a terminal Linux shell commands using unzip. Once that's done, then we should have the native Parquet file that we generated from part 1. And we can kind of display some useful statistics here just to make sure that the data looks proper. Here I actually grouped it by the cropland data layer label and the year, just to kind of see the data distribution of our labels. And they all look correct. As expected, we have a majority of soybeans, rice, corn, and cotton labels, along with some woody wetlands in this region. So the data looks good. Looks like we loaded it in properly. So now the first step we need to do is to kind of split these Parquet files, which again are just directories of multiple separate files, is what a Parquet file system is. And so what we'll do is we'll actually separate the training files and the data files into train, val, and test splits. And we can do that using the native Parquet file structure as we partitioned by the year. And so since we want to split by the year, we can use kind of glob to kind of filter out all of the files that only exist in the year that we want. So for train, that would be 2021, for validation 2020, and test files for 2019. And so then once we kind of load the file locations, the data files that we want to load, the Parquet files that we want to load for data loader, we can kind of see how many files would exist in each data set. Next, we'll need to kind of define some of the project variables that the data loader will use. These will be constant variables as we create the data loader. First, we'll define kind of which buckets of the seed cropland data layers labels will exist and which ones we want to identify when we create our custom label. So the first one is we, like mentioned in the slides, we want to target kind of soybeans, rice, corn, and cotton. So we'll add that into its own kind of targeted cultivated crops list. We'll also want to identify all other crops as cultivated. And so this is the list of crops that exist in this area in our data set that are other crops that we'll identify as cultivated. And then last, we'll kind of create this label legend, which is just a nice human readable format for which index, which label is included in which index. This includes the uncultivated, which is all kind of urban areas as our label, cultivated, which is all the other crop types, the no crop growing, which is that special example where there is crops growing, but there's no recent vegetation in the image, and then our targeted cultivated crops list. Next, we'll define some of the kind of model batch sizes and time series bucketing size. These are just kind of parameters that you can tune depending on your use case. Here, what we're going to do is define a batch size of 1028, which is a useful batch size that we kind of tuned a little bit when training the model in part 3, and 1028 was a useful size. These next 3 parameters define how long the bucketized function will look, what view it is. In our case, we used a view of 120 days long with 5 days per bucket. And then using these, we can define how many images will be contained within each regularly spaced bucketized time series, kind of using these 2 parameters in this function. Okay, next, as John mentioned in the slides, what we'll be doing in this example, since all the data can fit into memory, we will load it all into memory using kind of the TensorFlow from tensor slices after reading it in with Pandas read Parquet. What this will do is read in all of the files that we filtered before as Parquet files in Pandas data frame, and then convert that into a TensorFlow data set, and then that TensorFlow data set will then be further processed using the map function in the next step. I do offer, so I did mention this is all in memory since this example does fit in memory, and for performance reasons, since we're working with a little bit limited compute in Databricks community version, this makes it so the code runs faster within this environment. But if your data, for example, didn't fit within memory, if it was too big, then you can do kind of a from disk implementation example where it will load in each file individually in the queue and not load it all in memory at once. And this is one kind of commented out since we won't be using it, but one code example of how you might be able to do that in your own kind of code implementations if your data did not fit in memory. The main differences here is that you can use the TFIO from Parquet instead of the Pandas reader to read the files, and then instead of loading kind of all the data as a TensorFlow data set, you can load all the files as a TensorFlow data set that will be read using the read Parquet file with the TensorFlow IO from Parquet with either the flat map function or the interleave function. And then that enables you to kind of queue each file from disk instead of from memory. But again, for this example, we were sticking with the in-memory implementation since it is a little bit more performant for Databricks Community Edition. Okay, so next we're going to define all of our kind of custom functions that will do the bulk of the work, including creating our custom label from the raw cropland data labels, and then bucket our time series, and then define our parse function and our filtering functions. So first, I won't get into all the details since there's a lot of code here, and I'll allow you to peruse and go into detail and run this and experiment for yourselves. But I'll go over kind of a high level of what each of these functions does and each of these steps. So in the create label, this is defining how we're taking the raw CDL labels, converting them into our own custom targeted label space. What this is ultimately doing is taking those predefined lists above and checking to see if the label, if the cropland dataland label is contained in our targeted cultivated crops list, then set the label to be the index of this list. So this would be 0, 1, 2, or 3, plus 3 to allow room for the other labels that we want to exist. Similarly, if it's not included in that, then set it as the other cultivated crop index. And if it's uncultivated, set it to 0. And then lastly, we can take in the cropland data layer and the SCL, the scene classification layer, to then specify our special no crop growing label and set that as 2 if the cropland data layer label is a crop that's growing, but there's no recent vegetation in the past 2 images. If that's true, then we'll set this as no crop growing and the label will be the integer 2. Next, we'll get into how we define the logic for the bucket time series. So this is when we're going to be taking our irregularly-spaced time series data and converting it into a bucketized version of regularly-spaced time series using the parameters that we used before of days per bucket and days in series. So the first step what we'll do is we'll be randomly sampling the time range for the imagery. So that time range of 120 days, we'll be taking a randomly sampled date range and filtering the data between that date range. We will grab all the data that exists within that date range. And then this is something special here that we will randomly sample without replacement those images within that time frame down to fit if there is more images that exist within that time series. If there's, like, for example, duplicate images, we will randomly sample without replacement those images down to a proper size. And this randomly sampling has some benefits, including kind of increasing the combinations of images that the model will see in the time series, which will help improve model training stability and generalization as well. If there's no images in the selected time range, we'll fill with 0 values. So if for whatever reason our randomly sampled time range has no data, no image data available, then we'll just fill that with zeros. So there will be no data, and then pass that along into the model. Lastly, now that we have this filtered, randomly sampled time range of imagery data, we will bucket the data based on their position in the time series using this function here. If there are multiple images in the same bucket, so if there are 2 images taken near each other that would fall in the same bucket that we define, we need to randomly sample or select one of those. And so that's what this code does here. And then lastly, we'll actually do that kind of bucketizing transform and padding the data with 0 values. And we'll do that with the TensorFlow scatter ND function is kind of doing the bulk of the work here. And then That will be kind of our bucketized and padded regularly spaced time series of imagery that will return from this function. Okay, now the parse function will kind of combine all of these functions and logic that we used to actually create the final pair of training data and label that the model will expect from the data set. And so the first thing that we do is, if you recall, the data is in byte string format in the Parquet file. So first we'll decode these from bytes into real usable values using the TFIO decode raw function. We'll also define some additional helper functions, including like the days from the start of series, which will be used kind of in the future steps, like for the bucketizing functions. We'll define that here. Additionally, if you wanted to do some feature engineering or compute other variables for debugging purposes, you could do that here. For I compute the normalized difference vegetation index from our band values just for debugging purposes. This won't be used by the model, but it's useful to kind of validate our data and visualize it in a time series format. And so we'll see some examples of that later down in the code. Then we will bucketize our time series data after we've decoded it using the function that we defined above, and create our custom label, and we'll define that as Y. That's a common nomenclature to do so in machine learning. Define our label as Y. And then lastly, during training, we want to normalize the data. And so this next step will be normalizing the data. Additionally, if we're in training and we want to only use the band values for training the model. And so we will select the first 12 features, which is the first 12 bands. If we're not normalizing, then we'll just kind of pass it through, and this will be used for debugging. And we'll just kind of pass all the data out if we're not training the model, which will be useful for if we want to debug our training our data loader. Lastly, we will one-hot encode the labels and then actually apply the normalization of the data values here. Importantly, we will need to pre-compute the mean and standard deviation values for each of the band values, and we'll do that in the next step. And I'll show you how to do that. But they were pre-computed here. I've already done that kind of step ahead of time. And so then once we have the mean and standard deviations for each of the feature columns, then we can apply the normalization. And importantly here, we only want to do the normalization on the non-padded value, the non-zero values. And so we kind of can apply a mask here to ignore those zero values when we go and normalize the feature values or the band values. And then lastly, we'll return X, which is our training data, and Y, which is our training label. The last function that we need to define is our kind of filter function. The only filtering that we do in this example is filtering out kind of the double cropping labels, as we just don't want to predict on those. And so this is one method that we can do that using the TensorFlow strings regex function. We can take the CDL labels and filter out any CDL labels that contain that double text. So now that we have all of our custom functions defined, we can put all that together and define our final TensorFlow training data set using the exact same code that we had in the slides, where we'll take kind of the training data set of files. We'll filter the double croppings, we'll shuffle the data, we'll then map our custom parse function, specifying that we want to normalize. We're going to be using this for training. So we do set normalization to true, so it only passes the 12 band values that we want for training, and we'll normalize them. We will set parallel calls to TensorFlow AutoTune to improve performance. We'll then batch based on the patch size that we specified before, and prefetch to improve performance. And we'll do the same thing for the validation set as well. We can view an example output of the XY pairs using kind of this next iter on the train data set. As these train data sets, they are lazy loaders, and so they're actually Python generators, and so we can You can't index them directly, but you can kind of iterate generators in Python using this code here. And then we can see kind of the example of the data with the X being a TensorFlow tensor of shape 1028, which is our batch size, 25, which is our regularized length of bucketized time series data, and there are 12 bands, satellite bands from Sentinel-2. And then our label associated with that, which is our one hot encoded values or labels, custom labels that have shape of 1028, which is our batch size, and 7, because we have 7 labels. So next, I did kind of want to demo, now that we have the training data sets defined, I did want to compare the performance improvements of loading your data with parallelization and prefetching, and comparing that when you don't specify parallelization and prefetching. So for this test, I just define one data set that doesn't have parallelization and one data set that does have parallelization. And then to test the performance, I'll just kind of run a very, very small, simple model with just one kind of dense layer that's the size of the label outputs, and then run those through the model with one epoch just to test to see what the performance differences is. And we can see with the no parallelization example, the one epoch takes about 46 seconds at about almost 600 milliseconds per step. And the parallelization example runs at 36 seconds with 436 milliseconds per step. So we can see that there is a noticeable speed improvement by using the parallelization techniques. And especially if you run this outside of kind of the Databricks community environment with a CPU or compute that has many more CPUs than 2, parallelization will help you even more in those cases when you're training this on a kind of beefier computer. So I mentioned in our data loader, there's one last step that we need to do, which is compute the mean and standard deviation so that we can enable normalization of our data. And so what we'll do here is we'll kind of create a separate kind of test data set where we don't define the normalization because we want kind of an unnormalized data set to then compute the mean and standard deviation of that unnormalized data set. We will loop through this data set to kind of cache that raw data values and then reshape the data just to get the imagery values because we don't care about the other data that gets passed through it, including like the NDVI, et cetera. And then once we have kind of our band values, then we can compute the mean and standard deviation of our non-normalized data set. And again, we want to ignore kind of the padded values. So we're kind of masking out and ignoring 0 values from this calculation. And this results in the means and the standard deviation values for each of the 12 bands. So what you would do after you kind of run this is you can copy these values directly from here into the mean and standard deviation values that are defined up here. And I've already done that, so I won't do it again. But you would do that for both the means and the standard deviations defined here. And these are just constants that that you don't have to change. You only have to do this once. You don't have to change it after you set them the first time, unless your data set changes. So that is our final defined data set. So now that we've defined kind of all this logic and we have our data set, we're going to want to kind of do some visualizations just to confirm that everything is working as expected. So the first thing I want to test is to see if the normalization is working as expected, if the data values appear to be within a reasonable range. So we're going to kind of compare the normalized data set with the non-normalized data set using violin plots. And we can see the first plot is the normalized data set distribution. We can see that all the values are somewhat centered around 0 with some differing tails, but that makes sense. And this looks as expected. This looks like normalized data. And then we can compare that to kind of the non-normalized data set with the norm equals false filter in the parse function. And we can see that, yeah, absolutely, these are non-normalized data with very large kind of values. and with different kind of distributions. And so this also kind of shows why normalization is necessary. But yep, we can confirm normalization worked from this plot, so that's great. It also, since we have a custom label function, we want to see, what's our distribution in our final labels, as it will differ from the, raw cropland data layer labels. We can see we have a good amount of uncultivated and no crops growing pixels, which makes sense because the bulk of most of the year there's no crops growing, and so we're going to have more kind of labels in total in our data set where there's no crops growing. Cultivated, again, there's not, it's all other crops. The majority of crops in this region are soybeans, rice, corn, and cotton. And so the cultivated, like things like peanuts or winter wheat, are not as common. So looking at this all makes sense given what, the label transforms that we defined. And then lastly, we'll plot kind of some time series data to check that our bucketing function works as expected. And so we can go through kind of we'll use our non-normalized data set for this, just so we can visualize the NDVI values, which will be useful for kind of plotting this in a time series. And we can see if we run this, and we'll give 9 examples from the training set. But we can see, similar to the plots in the demo or the slideshow, we can see a time series of images that range from 0 to 25 consistently. And there's 25 images in our defined 120 time range with bucketed days of 5. We can see this is a soybeans example, and it's properly labeled. This looks like a kind of a soybeans, or something's definitely growing here. And we have a recent vegetation pixel for the last 2 images that we have. So this is properly labeled as soybeans. This example, however, we have a no crop growing, and we can see something was growing here. However, the past 2 images that we have are not vegetated, and so this is correctly identifying this as no crop growing, or this looks right. Additionally, it looks like our padding of values is being applied properly, and everything kind of looks good here. Importantly, it is useful to know that, again, we are doing some random sampling of the data, and so if we run this again on our data set, we're actually going to get different plots because of that kind of random perturbations that we're doing in our training data set to improve kind of model generalization. We're going to get kind of different data every time, so it's not going to be the same. So this is also useful to kind of maybe run this a couple times just to see that and confirm that we are randomly sampling and we are getting different results every time. But this is just another good way to just do another gut check to make sure that the data set is loading and doing the proper transforms that we want before we actually go into model training. And so that's it for the code demo. For part 2, next up, we will do the model training using this data set that we defined here. So yep, thanks for joining. Back to you, John.
All right, thank you, Erik. To summarize what we've learned today, we've created a very custom but highly efficient queue to load data in TensorFlow datasets. And specifically, this queue was focused on loading data from the Parquet files that had both cropland data layer information and Sentinel-2 information from our part 1 of this series as inputs. We talked about some of the functions that TensorFlow datasets have, such as the map, shuffle, batch, and prefetch functions that optimize the performance while doing a lot of the work to preprocess the data. We talked a little bit about how we are using some functions like decode raw to convert the byte streams that we stored the data in from part 1 back into a format of data that's usable for modeling. And we talked a lot about preprocessing steps. So specifically, some things from that would be splitting the data into training, validation, and test data sets to avoid data leakage and track if the model's overfitting, and also test generalization of performance. We normalize the data for training stability. We bucketed the irregularly spaced time series data into regular spacing intervals so that it could be modeled with a 1D CNN. And we modified the CDL target variables so that they would align with what's needed by the model training code. Looking ahead to part 3, we're going to train a 1D CNN off of this data. So by using the data loader that we've created here, we're going to be able to finalize and close the loop on this series with a model that can predict crop type from Sentinel-2 in real time. We're going to show how to model to track the model performance in Databricks using TensorBoard during the training process, and we'll finally test the results by visualizing the model predictions in various ways. Thank you.
Thank you, John. Before we transition to the question and answer session, I want to remind everyone there will be one homework assignment which you will be able to access from the training page on March 19th. Answers must be submitted by Google Form with a due date of April 1st. To receive a certificate of completion, you must attend all 3 live webinars and complete the homework assignment by the deadline. You will receive a certificate via email approximately 2 months after the completion of the course. Below is the contact information for Dr. John Just and Erik Sorensen, along with links to the ARSET website and social media. We hope you'll sign up on the ARSET listserv to receive notifications of future trainings, and follow us on Twitter for announcements pertaining to NASA's Earth Sciences. We will now transition to the question and answer portion of today's training. Please enter your questions in the question and answer box, and we will get to them in the order that they were received. We will post the question and answer document to the training webpage before the start of next week's training.
Okay, hello all.
Hey, John. Hey there. I want to thank everybody that's been submitting their questions. We've gotten some really good ones so far. So again, we do encourage those that are online, please do submit your questions to the Q&A box, and we will try to get through all of them in the next 23 minutes or so. So jumping right into it, question 1, how do we determine the best data set for training and testing the machine learning model? The partition of the data into training and testing is usually done randomly using a random state.
Yeah, this is where domain expertise definitely comes into play. If someone's kind of naive about, the nature of this type of data, they may kind of approach this in an incorrect way. If you randomly sample all your data across time and space in a very naive sense, you're going to get what we call information leakage, and therefore your model will actually it'll overfit to patterns that aren't generalizable. And so it's very important to make sure from a data selection standpoint, first of all, of course, you want to match whatever your goals are. You want to match the distribution of your data as closely as possible. So if your goals are to detect certain crop types, you should definitely focus your training data on that. But beyond that, when you do split up your training and test and you're randomly sampling it, so to speak, you want to make sure that you kind of cluster areas together. So areas or time frames. So one way we do this is we kind of say, all right, we're going to make 2019, we're going to use all the same area, but 2019 will be our training data, and then we'll use 2020 as validation and 2021 as test. If you were to do this more extensively, you might want to say, okay, let's use 2017 all the way to 2020 as training, and then validation and test could be 2021, 2022, something like that. But you really want to avoid information leakage. Otherwise, you're going to overfit, and your generalization is going to be more poor. And when you look at your validation, your testing data, you're going to think it's performing better than it actually does, and when you apply it in reality.
Great, thanks, John. Question number 2. On slide 22, regarding the overfitting chart, he mentioned that at a certain point, you can early stop the model in order to avoid overfitting. How could the model be stopped when it is already running? Would this not crash the process? Do you need to include the stopping condition in the parameters of the model so it stops by itself?
Yeah, so TensorFlow has what they call callbacks, which can add some additional functionality during the training process. One of these modules that they provide here in the callbacks is this ability to early stop training. It'll basically track the validation metric or any other metric that you define, and if it doesn't improve over a number of specified training steps, it will stop the training and then save the best performing model. So yep, we'll get into more details of this in part 3, but we do utilize or use the early stopping callback in the training process to do this.
Thank you, Eric. Question number 3. In the last slide, how is the value of NDVI between 0 to 100? The value of NDVI lies between -1 to 1. I think I missed something, so I just want to clear this up.
Yeah, so in the code, we just kind of scaled NDVI values by multiplying them by 100. So we actually got a range of -100 to 100. But then for graphing purposes, we narrowed the range down to 0 to 1. So yeah, the scaling to 0 to 100 doesn't really mean anything in a meaningful sense. It was just for kind of visualization purposes.
Great, thanks, Eric. Question 4. Hello, please, I don't have access to the database file database on Databricks. Could you check the access?
Yeah, this is a question we got in the first session as well. And so what you want to do is we provide a link here, but there is to get that toggle where you can actually toggle to the Databricks file system when you're looking at the catalog, you need to enable it. And so we have some instructions here we linked that you can go to enable the DBFS toggle.
Great, thanks, John. Question 5. Does this data work if we want to focus on flood damage assessment on crop monitoring?
Yeah, this is a good question. Like extending this approach to, and the intention was always to build it this way. Extending the approach to other targets is certainly doable. The only thing you really need to do here is, it does require domain expertise. Again, there's a part to this that you have to make sure your training data considers the challenge of this task. So, I think the person that we were talking with is looking at like Pakistan. And so in Pakistan, what you're going to want, and you're dealing with rice. So rice is a field that is a crop type that actually typically floods normally anyways to water the crop early on. And so you're trying to distinguish between natural flooding and natural unplanned flooding, and then some type of agricultural controlled flooding of the field. And so some of that could be, captured probably in the time series, in terms of when the actual flooding happens and the extent, the time that it actually remains flooded, as well as some of the depth. It might be especially deep, which causes different reflectances. So my assumption is all you need to do here as a starting point is just get your targets down so you know where, what the difference, you're trying to classify flood damage versus not flood damage, right? So the first thing to do is get your targets situated so that they kind of match the format of the CDL data. And that format's just intended so that you can subsequently follow up and acquire all the Sentinel-2 data and then train your models. So I think as long as your target's set up properly, this should be, it should follow the exact same process we've laid out here.
Thanks, John. Question 6. Do we need an AWS account to run these notebooks in Databricks?
So yeah, the Databricks Community Edition, you don't have to worry about setting up an AWS account or Azure account. It'll take care of all that for you. If you do end up using a paid Databricks account, you go that route, you would have to set up an AWS or Azure account to be connected to the Databricks so you can set up compute in either of those environments. But yeah, for this training, if you're using Databricks Community, you don't have to worry about creating a separate account.
Okay, thanks, Eric. Question 7. I want to focus on flood monitoring and crop damage assessment using remote sensing. Looks like they want to use some optical and radar data and high-resolution imagery with planet smallsat constellations. So are crop types important?
Okay. So let me. I didn't have a chance to look at this, but if you are okay, I want to focus on flood monitoring. Okay. Yeah, and I think this was actually the same I think this was actually an extension of the same question that was asked earlier regarding flood monitoring and using our using the same process to predict that. So I think I covered that in my last answer where yeah, crop type is important because of exactly. I mean, this is domain expertise, but it's in your case. You're looking at a crop like where there's a lot of rice in Pakistan. So rice naturally, you're controlled flooding the field typically. So, you're looking at a situation where there is kind of a flood in the field typically, and you're trying to distinguish that from like an actual damaging, uncontrolled natural flood. And so, in that case, you do have to consider the fact that your crop type is a very, has an unusual characteristic about it. Because if you were to look at corn, it's not ever typical to have that. So any type of water in the field, in a cornfield or a soybean field, is a problem that's not expected. But in rice, it's expected. So yeah, you absolutely do want to consider that.
Great, thanks, John. Question 8, out of curiosity, why do you use the term bucket instead of the more commonly used bin or temporal window composite?
Yeah, so there's no particular reason we use the word bucket versus bin or a temporal window composite. The meaning here is the same. In my opinion, bucketize is kind of more fun to say than binning, but I think that's maybe why I lean toward it.
Awesome, thanks, Eric. Question 9, can we use the same code like an example with our sample data?
Yep. That was the intention of all of this. Kind of similar to the previous flood monitoring one that we were talking about. Just make sure that your target data, whatever it is, if it's regression or classification, just get it formed in the same format that we showed in part 1 of this series, the first script where we're acquiring the CDL data. Run your script or run our typical script on that. Get the CDL data. It only takes a couple minutes, and look at the output of that and get a feel for what the format of it is, because everything downstream uses that to acquire Sentinel-2 data. So if you get the format just matched like that, everything downstream is going to work fine.
Great, thanks, John. Question 10, did you try to normalize with all data versus only training data?
So no, we should only calculate the normalization factors on our training data set, not the validation and test sets. So leave those out when calculating the normalization factors, the mean standard deviation, and then you would apply those mean standard deviation values to the same ones that were calculated on the training set to the validation and the test data.
Great, thanks, Eric. Question 11, will CDL monthly data be released soon? Is it feasible?
I mentioned this. I did have an answer to this in the Q&A. It was a good question. Like, I'm not aware of them being thinking about releasing a monthly version of this. The two reasons I'm aware of them not doing this more often, one of those being just the cost to run it across the entire United States for the given resolution and higher frequencies. And then the other one being that markets are sensitive to what crops are being grown. And so, I don't think the USDA is trying to provide information that, would cause markets to react to too significantly in this case, to my understanding. So.
Great, thanks, John. Question 12. Are the same means and standard deviations used for both the training and test set, or is it recomputed given a new raster?
Yeah, this is similar to the previous question. Just calculate the mean standard deviations on the training set, and you'll apply that same calculated mean standard deviations from the training set on the validation and test data and any other future data that the model will run inference on.
Great, thanks, Eric. And question 13, what sensor do you recommend using, radar or optical, to monitor and predict land use and vegetation in the central zone of Mexico? And what other sources of information do you recommend combining?
Yeah, again, a great question, and you're jumping ahead to what next after this. I'm going to say just start with doing, and I didn't finish the entire thought here, but start with kind of figuring out what type of vegetation, what type of land use do you typically expect to see there, and try to acquire that from the CDL. So build your model just based on optical, like Sentinel-2 is a starting point, like we've shown here. Get something working. Make sure it's kind of doing something reasonable for that area. And once you feel like, okay, I've been able to apply this to my area, then you can start adding other sources if you feel like that's going to help improve the accuracy of your model. But there may not be a need. I mean, I don't think like the CDL for the U.S. really doesn't use radar, to my knowledge. I think there's one in Canada for land cover predictions that does use Sentinel-1. But I don't think there's a there's the CDL does pretty well without it. So you may want to focus on just optical at first. So maybe if you get Sentinel-2 working, you feel like you need higher temporal resolution, maybe add in a Landsat, because they do have a particular data set available where they've it's available from I can't remember if it's USGS or ESA. Maybe Sean, but they've basically combined Sentinel-2 and Landsat, and they've kind of reconciled the differences between those band values to align them. I forget what they're called. Maybe Erik, do you remember what the name of that data set is?
Yeah, it's HLS, Harmonized
HLS.
Landsat Sentinel.
That's it. Yes.
Yeah,
The Harmonized Landsat Sentinel data set. Yep.
And we'll put a link to that in the chat so everybody can go and explore for themselves.
Was there any other questions?
Just dropped a link in the chat to the Harmonized Landsat Sentinel. Yeah, we do encourage, there's still about 10 minutes left. So if anybody has a question that they've been wanting to ask and for whatever reason they weren't able to or did not want to submit it until now, please do. We encourage questions. There's no bad questions, so please do ask them. I also want to let everybody know that following next week's third part of the webinar series, there will be a survey sent out to all the participants. So we do strongly encourage you, when you receive that survey, please do submit it, fill it out and submit it. It will take no more than 5 minutes. And it's incredibly valuable for the ARSET team, for John and Erik to get the feedback. And it really helps to improve all future training. So the more feedback you're able to get us, it really does excuse me. It really factors into how we plan our trainings, what trainings that we try to offer, and also how we prepare for those trainings. So we do encourage that when you do receive that survey, please do take the time to fill it out, and we would greatly appreciate it. So that will be following next Tuesday at the last part of the webinar series. So it looks like we are getting
Dorsa, yeah, we got one in here. So Dorsa asked, is the planet data 3-meter resolution better for predicting crop type than Sentinel-1? It really depends on your use case. It depends on what your limitations are. If you're in an area, so like I'll give you an example. Some places in Brazil have so much cloud cover that optical satellites almost never can see the area. And so in that case, even the high temporal spatial resolution of planet isn't going to really matter, because you can't get through and see the area. So you're going to want to use Sentinel-1 there. In other areas where you have pretty good visibility of the land, you're probably going to want to bias towards, if you have access to planet, you probably don't want to bias towards that because of the high spatiotemporal resolution. So I don't know, that'd be my thoughts.
I'd also say if cost is important for your use case. Planet's not. Planet does cost money, but Sentinel-1 is not. So again, that's another kind of factor to consider.
Great. It looks like we got another question, 15. About the approach on training using 1 year of data, testing another, validating another year. This has the complication of drought years, which can complicate the classification. Is there an approach that considers training, validation, and test with mixed years, considering the same region sampling?
Yeah, I think that's a great question, and there was a similar question asked earlier, kind of along these lines, where it's asking like, how do you decide on your training and test data? And that's where it's really important to have some domain knowledge. When you look at the fact that there can be very large seasonality changes in temperature and the precipitation available, you kind of, and you expect that to happen. You know that you need to sample probably across years and include those in your training data. So, as an example, usually what we like to do is, historically, if you can go back and use the 3 to 5 years at least in your training data set for the areas that cover, the crop types you're interested in. If you can do that, you are generally going to be covering, a little bit wider range of seasonality differences, and you're going to make your model more robust for that. So, that's what we recommend as a rule of thumb or as a starting point. Certainly, if you get some really, really big outlier, drought year that shows up that you weren't expecting, or it's really hot for whatever reason, unusually hot, and that somehow causes a different response in the crop phenology, how it grows, that could cause some issues. But as much as possible, try to sample across as many years as you can in your training data, while still reserving enough to test on.
Well, John and Eric, I think we've gotten through all the questions. Thank you to everybody that did submit them. We really, really appreciate all the questions that came in. As we wrap up the second part of the webinar series, John and Eric, maybe John, if you can go first, maybe any closing thoughts or comments on today's webinar as we head into next week.
Yeah, thanks. We're really excited to see everybody from all over the world join and ask some really great questions. I love to hear, what some people are doing. Really enjoy being able to share this stuff with everyone. Please reach out. Let us know if you got any other questions, or let us know what you're working on. We're always interested to see and hear what people are doing.
Yeah, I'll just ditto that. It's been amazing to see all of the engagement in the chat, a very engaged chat for a webinar in my experience. So thank you everybody for your engagement and your questions. And yeah, we're definitely excited to see what people do with this training in their own applications. So yeah, definitely reach out and let us know what you're doing.
Awesome. Yeah, John and Eric, thank you both so much. Also want to acknowledge the ARSET team that's been working tirelessly in the background to help promote and put on this webinar series. That's Natasha Johnson-Griffin, Brock Blevins, Selwyn Hudson-O'Doy, and Sarah Cutshaw. So thank you to the ARSET team. I also want to thank all the participants today for joining, and we look forward to seeing you all next week at the same time. So take care of yourselves, and we'll see you next Tuesday. Bye.